All right. So welcome to Signal Consistence um, lecture. Today is Tuesday, 11th of April, and I'd like to thank you for those who can attend today's lecture, and for those who cannot, you can always. I'm gonna record and put it in a clip and post it on Google Classroom so you can watch later in case you cannot attend the online meeting here. So last time, okay, we began talking about Fourier transform. Okay, the definition of the Fourier transform is we start with a signal x. Okay, the signal x is a time domain signal. It's a time signal, meaning that the value of x changes with time, and we're going to perform something on the signal x. Okay, uh, that is we're going to take the Fourier transform of the signal x, and the definition of the Fourier transform is the integration of the signal x multiplied by e to the negative j omega t, and we integrate it over time with respect to time, and its integral is over the whole range of time, meaning that it starts from negative infinity to infinity. That's the definition of the Fourier transform. Now, once the integration is carried out, the variable t will disappear, and we will have only the variable omega left. And so the integration here, the integral will be a function of the frequency omega. So that's why we denote the Fourier transform of the signal x by the capital X, another function x that is a function of omega here. Okay, that is the definition of the Fourier transform. Uh, on the other hand, if we know the Fourier transform x of omega, we can always reverse the process to find the time domain signal xt by taking what we call the inverse Fourier transform. And the inverse Fourier transform can be determined as follows. Okay, we're going to denote it by f to the minus 1 here. That denotes the inverse Fourier transform, but now it is x of omega because we're going to take the inverse Fourier transform of x omega, and the definition of the inverse Fourier transform is 1 over 2 pi integration starting from negative infinity to infinity x of omega e to the j omega t d omega. And when the integration is carried out, the result will be the time function x of t. Now it turns out that these two functions are unique, meaning that knowing one can uniquely determine the other. So they form a Fourier transform pair. So uh, x of t and x of omega form a Fourier transform pair. Okay, this Fourier transform pair means that knowing one can uniquely determine the other. Okay, so we can write x of t and uh, two arrow headed and x of omega here to indicate that there are uh, uh, Fourier transform pair, and also the Fourier transform of the inverse Fourier transform of actually yeah of omega x omega will be equal to x of omega here. Also, the inverse Fourier transform of the Fourier transform of x of t will be x of t. So this is what it means by uniquely determine the other. All right, so this is very important to understand. This means knowing one can uniquely determine the other. The important word is uniquely. Okay, the important word is uniquely. There is no ambiguity in determining the other if you know one. Now, a couple of examples. Okay, we did a couple of examples. We uh, we found that the we found last time we found a couple of Fourier transform pairs. We know that the delta unit impulse signal has a transform pair of 1. Okay. We also found that the rectangular signal of width t has the Fourier transform pair of t sin omega t over 2. So this is what we had from the previous lecture. We also found that uh, the constant 1 has the Fourier transform pair of 2 pi delta. Okay. Also, the cosine signal of frequency omega has the Fourier transform pair of 1/2 delta at minus omega 0 and delta at omega 0. Okay, now let me go back momentarily to say that Fourier transform can represent time signal. Okay, it is a representation of time signal in the frequency domain. Now, it tells you the presence of a signal in certain frequency ranges. For example, if you want to know if a particular time signal has its presence in some frequency, at some frequencies, then you'd have to look at the Fourier transform of it to see if the Fourier transform of it has some value in that particular frequency that you're looking for. For example, if I want to know if I'm interested in the delta unit impulse signal, and since because the unit impulse signal has the Fourier transform of 1 across all the frequencies, then I know that the unit impulse signal has its presence at all frequencies equally. Okay, because the Fourier transform is one and it is the same across all the frequency range. So it has its presence across all the frequency range equally. Okay, no particular frequency is stronger than any other frequency. On the other hand, uh, the constant signal one has only its presence at frequency zero. Okay, it doesn't have any presence at any other frequency except only at frequency zero. All right, so we can say that the DC signal, which is one, has only one frequency presence, and that is frequency zero. Okay, so let me take a note here. Only at omega equal to zero is present. Okay, so it has only one component, which is at omega equal to zero. So here, whereas here the it uh it is present. This signal is present. The unit impulse signal is present across all frequency. Okay, equally. And as for the cosine, it is present only at omega equal to plus and minus omega zero. Okay, which makes sense because after all, the sinusoidal signal has a frequency of omega zero, right? So it should be present only at that frequency, which is omega zero. Okay, and uh, we uh, we discussed some properties of Fourier transforms. Okay, basically we discussed about the first property, which was linearity. The linearity property states that if you multiply a signal by a constant a, okay, added by another byt, then the result from this linear combination has the Fourier transform of the same linear combination of its respective Fourier transform. In other words, if you want to take the Fourier transform of this linear combination, then you can take the Fourier transform of each of x and y and perform the same linear combination operation on the Fourier transforms x and y to get this result. Okay, that is linearity. And the second property that we discussed last time was time shift. Time shift property states that if you shift the signal x in time, then its Fourier transform is just the Fourier transform of x multiplied by the complex exponential. Okay, the time shift to zero will appear as the exponent of the complex exponential, e to the minus j omega, and then the time shift that you perform here. Right. And then the third property is called time scaling. that we talked about last time. Time scaling states that if you scale the time signal, if you do the time scaling of a time signal x of t by multiplying the t by the constant a, where a is not equal to 0, then its Fourier transform pair would be 1 over the absolute value of a and the Fourier transform of x. Now it is omega over a. So what this means is that if you expand the time signal x, then the Fourier transform, the resultant Fourier transform would be to shrink or make it narrower in the frequency domain. You know, on the other hand, if you shrink the signal x in the time domain, then in the frequency domain will be expanded. So expanding one domain will mean shrink in the other domain. They go inversely proportional to each other, right? They go against each other. If one domain is expanding, then the other domain will be shrinking, and vice versa. Okay, so that is time scaling, where a is not equal to 0, of course. And the fourth property that we talked about last time was duality. Now, duality is very important in finding Fourier transform of some signals that that are not easy to find directly. And it goes like this. If x of t has the Fourier transform of x of omega, then x of t here would have the Fourier transform of 2 pi x of minus omega. Now, the way to remember this is x of t here will move across to the right, and we have to replace t with minus omega, and the capital X here will move across to the left and replacing omega with t. So it goes like this. Now this is very useful. For example, an example of how to use duality is that since we know that delta has a Fourier transform of 1, then if we move 1 across to the left and delta across to the right, we're going to get 1 as x of t has Fourier transform of 2 pi delta minus omega. Here, you see? Can you see? We can apply this to delta. So we move 1 across to the left and delta across to the right. Then we can get this Fourier transform pair. And because delta is an even function, so delta of minus omega is equal to delta of omega. So that is 2 pi. That is 2 pi of delta omega. So this is how to determine the Fourier transform of one, of a constant. Also, another one is, since we know that rectangular signal of width t has Fourier transform of t of and sinc omega t over 2, Then we can move this over to the left and move this over to the right to get t sinc, and we replace omega with little t to get big T and little t over 2 has a Fourier transform of 2 pi, and then we replace the variable t with minus omega here, and this will mean that uh, this will mean that the sinc function of beta t by changing variable has a Fourier transform pair of pi over beta and rectangular omega over 2 beta here. All right, and this is very useful. Okay, now let's do some plotting here. Okay, we had the sinc signal, all right, on in the time domain. So this is sinc beta t. Now sinc of beta t has a plot, has a graph that looks similar to this. This is the shape of a sinc signal. Okay, now the zero crossing is at uh, pi over beta here, and this is 2 pi over beta. This is 3 pi over beta. Now this is minus pi over beta. This is minus 2 pi over beta. This is minus 3 pi over beta. Now these are the zero crossings of the sinc signal, and this is 1. So this Fourier transform pair tells us that the frequency spectrum of this time signal is a rectangular pulse. So this is plotted with respect to omega. We get this. Now, the rectangular here is 2 beta wide. So the parameter beta here will be beta here and minus beta here because the width is 2 beta. So it is beta, oops, sorry. It is beta here and it's minus beta here, 0 here, and the height is pi over beta. So this is a spectrum of the sinc signal here, all right? Notice this is in frequency domain. Okay. Now, the next one that we talked about last time was, sorry, was what? Was frequency shifting. Frequency shifting. Now, frequency shifting is this. Okay, we multiply the time domain signal by the complex exponential e to the j omega 0 t, and the Fourier transform of the result would be to shift the frequency spectrum of x to the right by omega 0. So shifting the frequency of the spectrum to the right by omega 0 by frequency omega 0 means that the time domain has to be multiplied by the complex exponential e to the j omega 0 t. All right, and let's look at some example. This example is called modulation. In communication systems, we are often be presented with with a signal that looks like this. We have x of t equal to some signal m of t multiplied by cosine of some frequency omega 0 t here. This is called modulation. Whenever you see this signal, it means that we call it the signal m modulated with the sinusoidal frequency at frequency omega. So this is called signal m of t is modulated with the sinusoidal at frequency of the knot. Okay. Now we're gonna look into the spectrum of xt. So we can write cosine in a form of complex exponential. So since cosine of omega 0 t is 1/2 of e to the j omega 0 t plus e to the minus j omega 0 t. Okay, we plug it in to this modulation equation. We're gonna have, once we do that, we're gonna have x of t equal to 1/2 of m of t e to the j omega 0 t plus m of t e to the minus j omega 0 t. Okay, and then we know that if we take the Fourier transform, this term, which is mt multiplied by a complex exponential in the frequency domain, will be the spectrum of m shifted to the right by omega 0. And this term is the mt multiplied by another complex exponential, but then the frequency is minus omega 0. So we have to shift the spectrum of mt to the left by omega 0. So that means that the spectrum of x by frequency modulation, by frequency multiplication, by frequency shifting property would be 1/2 of m omega minus omega 0 plus the m omega plus omega 0 here. So what it means is that if you multiply a time signal by a sinusoidal at frequency omega 0, the resultant signal, the spectrum of the resultant signal will be shifted to the frequency omega 0. Okay, so that means that, for example, if the spectrum of m, if the spectrum of m is this, suppose the spectrum of m is this. Okay, this is let's say this is omega m and minus omega m, and let's say this is 1. Then the spectrum of x, after we multiply the time signal mt by cosine at frequency omega 0, okay, the resultant will be this signal, this spectrum shifted to the right and to the left, but the amplitude will be half. So it will be this. This is the one shifted to the left, and the other one is shifted to the right. Here. Okay, and the height is 1/2, of course, and the shifting frequency is omega 0 minus omega 0. Okay, and this is, of course, minus omega 0 plus omega m. This is minus omega 0 minus omega m. Okay, and this is omega 0 minus omega m. And this is omega 0 plus omega m. So this is the result of modulation. Modulation means that we're shifting the frequency content of the signal. And in doing so, we're preserving the shape of the spectrum of the signal. Only shifting the signal. We are only shifting the spectrum of the signal, but we are not changing the shape of it. Just shift it to the left and to the right. All right. Now, the next, if you don't have any question, I would like to move on to the next property, and the next property is time differentiation, and that would be the sixth property. Okay. The sixth property is called time differentiation. Unless you have some questions, if you have questions, please don't hesitate to ask. I'm not sure if you're still with me. How many of you guys are still with me? How many of you guys are here? Oh, okay. See what? All right. You have any question? No? Okay. If you have questions, you can ask anytime. All right. Please feel free to interrupt anytime. Okay. Can I get it for now? Okay. Time differentiation. Now, time differentiation property goes like this. If we differentiate, if you take a first derivative of the signal x with respect to time, okay, and we take the Fourier transform of the result of the derivative, then the Fourier transform of the derivative would be just to multiply the spectrum of x by j omega. Okay, this is time differentiation. Very easy. Cannot. Okay, now if you do it twice, you can always do it twice, right? If you do it twice, then the result would be just multiply this guy with another j omega. Now, if you do that, we're going to get minus omega squared, right? X of omega. So if you do it many, many times, if you do it n times by differentiating x with respect to time n times by taking the nth order differentiation, the result would be just to multiply the spectrum of x by j omega squared to the nth. Okay, so this is this is this is time differentiation property. Now we can use time differentiation property to find Fourier transforms of some signals that are typically difficult to find directly. So let's look at an example of how to use time differentiation. Now let's look at the signum signal. The signum signal is defined as uh, x of t, and the notation for a signum signal is HGN, stands for a signum signal of t. It is a time domain signal, and the value of it is 1 whenever t is greater than 0, and -1 whenever t is negative. So it will indicate the value of the signum signal indicates whether we're looking at a positive time or negative time. If the value is 1, then it means that we're looking at a positive time, and if the value is negative 1, then we're looking at the negative time. Now, the question is, we'd like to find the Fourier transform of the signum signal. Okay. We first notice that if we define, sorry, we want to find x over omega, the spectrum of the signum. I will use the word spectrum and Fourier transform interchangeably. Whenever I say spectrum, it means that the Fourier transform, right? They can replace the other without any ambiguity. So the spectrum of x of the signum. Okay, we'd like to find the spectrum, or we'd like to find the Fourier transform of the signum signal. Now, so to do that, we notice that uh, the signum signal x is equal to 2 times the unit step signal minus 1. Now, how is this so? Okay, if you don't understand this, you can plot the graph of a signum signal. Okay, if you plot the graph of the signum signal, you see that it is 1 when time is greater than 0. So it is 1 here, and it is -1 when time is less than 0. So the graph of the signum signal looks like this. It goes from -1 to 1, depending on the time. So this means that the height of this is 2, right? It goes from -1 to 1, so the height is 2. That's why we multiply 2 to u, and we have to push it down 1 unit. So if the time axis is here, then this signal would be 2u, right? Would be 2u. But now the time axis is right here, so we have to subtract it by 1 to get this signal. So the signum signal is 2 times the unit steps subtracted by 1. And then once we notice this, we can take the time derivative of both sides. Now on the left hand side, we get dx by dt, right? Now on the right hand side, we get d by dt to ut, right? Minus d1 by dt. Now the latter term is easy because it is the derivative of a constant and that is equal to 0. Now what about the derivative of u? We know from chapter 1 that the derivative of u is delta t. So dx by dt would be only just twice the delta signal t here. And then we take the Fourier transform of both sides. This means that the Fourier transform of dx by dt is just twice the Fourier transform of delta t. Now, if you look at the Fourier transform of dx by dt, we know that it is equal to j omega x omega, right? Using the time differentiation, we see that this is just j omega and the spectrum of x. Now, on the right-hand side, we know that the delta unit impulse has the Fourier transform of 1. So the right-hand side is 1. So that means x is 2 over j omega. But x is the spectrum of signal, right? So we know we have that the signal has the Fourier transform here of 2 over j omega. This is an example of how to use this time differentiation, time differentiation to find the Fourier transform of some functions that are not straightforward if you do the direct approach. Okay. All right. Now let's look at another example. This time we're gonna try to find the Fourier transform of a triangular signal. The triangular signal. Okay, the triangular signal is defined. Well, let's look at the graph first. A triangular signal is denoted by TRI. Okay, well, let's call it just X. Now the shape of the triangular signal is, of course, a triangle. Okay, and it looks like this. It is a triangle. Actually, it is an isosceles triangle. Okay, and it goes to the right by t, and it goes to the left by t as well, and the height is 1 here. This is what we call a triangular signal. So if you try to write an equation for it, right, we'd get, and by the way, we denote it by TRI. Okay, TRI stands for a triangular signal, and T over capital T here. So whenever you see this notation, it means that it is this signal, the triangular signal, that goes to the right by t and goes to the left by t. So the definition of it, the mathematical expression, when the time is positive, it is a straight line graph with slope of minus 1 over t. So it is minus t over big T, and the y-interception is 1, so plus 1 when time is 0 up to t here, and when time is negative, the slope is 1 over big T, right? So it is t over big T plus 1 when time is negative. Other than that, the value is 0. So this is a mathematical expression for a triangular signal. Let me move it a little bit to the left. Now let's try. We're gonna try to find the Fourier transform of a triangular signal. We will find the spectrum of the triangular signal. Okay. Now, let's if we try to do it directly using the definition of the Fourier transform, then we would have to do the integration by parts, which is not particularly appealing because it is rather complicated. So rather, we would like to take a detour. Okay, we would like to go around the definition and we'll try to find the Fourier transform using the time differentiation property. So we would start with the definition of x here, and we try to differentiate it with respect to time and see how it goes. So starting with the definition of the triangular signal, right? We differentiate it with respect to time. Okay. Now when we differentiate it with respect to time, when time is positive here, okay, 1 will disappear, right? Because 1 is a constant and the derivative of constant is 0. Now this one, if we take the derivative of it with respect to time, we're going to get minus 1 over big T, right? So it is minus 1 over big T when time goes from 0 to big T. Now when time is minus big T to 0, this one goes away, disappear, and this one has the derivative of 1 over big T. So we have 1 over big T when time is negative. And elsewhere, because the value of x is 0, so its derivative is also 0. Okay, now let's plot this graph with respect to time. If you plot this with respect to time, we will see that it is it is this. Oh, excuse me. Here. All right. It looks like this. So when time is positive, right, it is minus 1 over big T. So this is big T here, minus big T here, and this is 1 over big T. This is minus 1 over big T. This is 0. Okay, and so this is big T over 2. This is minus big T over 2. Okay, and so this one, these poles would be minus 1 over big T and rectangular of small t minus big T over 2 over big T. Because after all, if you look at this pulse, it is a pulse. Okay, it is a, a vertically flipped pulse, right? It goes downward. And the width of it, its width is big T. Okay, that big T goes here. and the center of it is at big T over 2. So big T over 2 goes here. So this is this pulse. Okay. It flips upside down, right? So that's why I have a negative value here. Similarly, this pulse, okay, this pulse is a typical pulse, right? And the width is of course big T as well. So we have rectangular 1 over T rectangular of T plus big T over 2 divided by the width, which is T here, right? So we plug it in to this, we're gonna get equal to 1 over big T, right? And then rectangular small t plus big T over 2 divided by big T minus rectangular small t minus big T over 2 divided by big T. Here. This one is this guy, okay? Whereas this one is this guy, right? Now, we can take the Fourier transform of both sides. The left-hand side will be the Fourier transform of dx by dt, okay? While the right-hand side would be 1 over big T, the Fourier transform of rectangular small t plus big T over 2 divided by big T minus 1 over big T Fourier transform of rectangular T minus big T over 2 divided by big T here. Now, the left-hand side is easy because we can use the time differentiation property, and we know that the left-hand side will be J omega times X. Okay, this is by time differentiation property, going from there to here. Now, what about this? Okay, to determine this, right? To determine this, we have to know that the Fourier transform of rectangular T over big T, right? We know that this is equal to big T sine, big T sinc of omega big T over 2. Okay, this is what we know from the beginning of this lecture. Now, but this is the time shifted version, right? So we can use the time shifting property to say that the rectangular of small t plus big T over 2 over big T would have to be equal to this guy, right? And then multiplied by complex exponential. Okay, multiplied by the complex exponential, which is e to the j omega. Now, the time shift, the amount of the shift is big T over 2. So big T over 2 goes here. So big T over 2. Okay. Similarly, the other one, which is rectangular, small t minus, this time it is minus big T over 2 divided by big T. It is big T sinc omega big T over 2 e to the minus j omega big T over 2. Okay, so we can plug these two guys into this equation and get this one is equal to 1 over big T, right? 1 over big T, and then we can pull the T sinc out of the parentheses to get T sinc omega big T over 2. Okay, and then the inside of parentheses are these two complex exponentials added together. So we have e to the j omega big T over 2 plus minus e to the minus big J, oh, not big J, j omega big T over 2. Okay, so we get this. Now, this we know from Euler, right? It is 2j sine of omega t over 2. So we have 1 over big T. Now T will be gone, right? T will cancel each other. So T is gone. So we have sin uh, omega big T over 2. Then the parenthesis is J2 sine of omega big T over 2. So we have this. We have this now. Now, I'm going to divide through by j omega, right? I'm going to divide through by j omega. So j will cancel. J will cancel. So I have x of omega, which is what we are looking for, equal to um, 2, I'm sorry, it is equal to 1 over omega over 2, right? And then sine of omega t over 2 and sin of omega t over 2. Okay, and then I recognize that this is omega over 2, right? And this is also omega over 2. So I should multiply by t, okay, to get omega t over 2, right? So I'm going to multiply by t here, and I'm going to multiply the denominator also by t. Okay, and I recognize that this is just sinc function of omega t over 2. This is the sinc function, right? So I have t of sinc omega t over 2. And of course, this one goes here unchanged. So I have sinc omega t over 2 again. Now, these two are the sinc function. These two are the same. So it is the sinc squared, right? So it is equal to t of sinc squared omega t over 2. Now, this is a solution. This is the answer. So in conclusion, I have the triangular signal that goes to the left by big T and goes to the right by big T has a Fourier transform pair of T sin squared omega big T over 2. Okay, so this is another Fourier transform pair that is obtained by using time differentiation. Now let's plot this. On the left hand side, I got the time domain signal, which is a triangular signal. So this is a triangular signal. Okay, and goes to the right by t, goes to the left by t, and the height is 1. And on the right, I have the sin square signal. Okay, this is the frequency domain signal, the spectrum of the triangular wave signal. Now it is a sin, it looks like a sin, but it is not exactly the sin signal because it is a sin square, so it is all positive value. And the shape of it, oh, to find the shape of it, I need to find a zero crossing again. 1, 2, 3, 1, 2, 3. Okay, this is 2 pi over big T, 4 pi over big T, minus 2 pi over big T, minus 4 pi over big T. Okay, now these values are determined by setting the parentheses equal to k pi, right? This is equal to k pi. So because when the parenthesis is equal to k pi, then the sinc will be zero, right? So there are the zero crossings of the sinc function, and then omega would have to be 2k pi over big T. So that's why this is when k equal to 1, this is when k equal to 2, this is when k equal to minus 1, this is when k equal to minus 2. Okay, and then I have to draw the sinc square, and the shape is something like this. This is a sinc square. Oops. This is a shape of the sinc square. Okay. Of course, the height is now big T. Big T comes from here. This is big T. Okay. Right. Okay. Now the next property is very important, and it is called the time convolution property. Time convolution property. Okay. Uh, which one is it? It it's going to be the 7, property 7. Property 6 was time differentiation, so property 7 is time convolution. So 7, time convolution property. This is a very important property, just like what we saw in the Laplace transform. Time convolution property goes like this. If you do time convolution between two functions, ht and xt, we're doing time convolution of h and x together. The resultant from the time convolution, taking the Fourier transform, would be equivalent. It would be equal to the Fourier transform of h multiplied by the Fourier transform of x. So the Fourier transform of convolution is the product of the Fourier transform. Okay, so the Fourier transform of a convolution, a time convolution is the product of the Fourier transforms. Just like when we did Laplace transform, very similar. Okay, for example, now let's look at an example. Uh, Example, okay. This example is called the ideal low pass filter. The ideal low pass filters. So what is an ideal low pass filter? An ideal low pass filter is linear time invariant system that will block uh, uh, high frequency components of a signal from passing through. So we have a low pass, I, we have a linear time invariant system. Okay, with a with an impulse response ht, which we call ideal low pass filter. LPF means low pass filter, and we feed it with a time domain signal x. Okay, and the output of this time linear time invariant system is denoted by the signal y. Now, the ideal low pass filter, okay, an ideal LPF is a linear time invariant system that blocks high frequency components of the input signal from passing through. It doesn't let the high frequency component pass through, okay? But the low frequency component will be able to pass through unchanged. The low frequency components will be able to pass through unchanged. So according to this definition, and according to the time convolution, okay, um, if we take now, but from chapter 2, right? From chapter 2, we know that the output signal is written as the time convolution of the impulse response of the system and the input signal. This is from chapter 2. Now, if you take the Fourier transform of both sides by time convolution property of the Fourier transform, the spectrum of the output will be equal to the Fourier transform of the impulse response multiplied by the spectrum of the input. Okay, so by the description of the ideal low pass filter, okay, we know that the function of h omega has to be a rectangular signal, a rectangular function here. It has to be a rectangular function. So this is h of LPF. Height is 1. Now this is omega m sorry, this is, let's call this beta, and let's call this minus beta. So you see, if omega, so so if h is described by this function, we see that the output would be, now if the frequency is between minus beta to beta, then the value of h would be 1, right? And so y would be x. So y would be x if omega is less than beta. But if the frequency omega is greater than beta, the value of h would be 0. So 0 multiplied by x would be 0. So it would be 0 elsewhere. So you see, if h here, if the Fourier transform of the impulse response is this rectangular function, then the spectrum of the output will be the spectrum of the input, exactly the same as the spectrum of the input whenever the frequency doesn't go higher than beta, and it will block the output. Okay, the output would be 0 if the frequency is greater than beta. So in other words, if the frequency of the input is greater than beta, those components cannot pass through because the output would be 0. So this means that if, so this is the edge of an ideal low pass filter. So this means that if we have the input, if we have an input signal that has a spectrum that looks like this. So if it's if the spectrum is a triangular shape, and we feed it to an ideal low pass filter, and the output, and the ideal low pass filter has the spectrum has the transfer function of this for beta and minus beta and 1 H LPF, and this is y. This is yt. So if beta is less than omega m, this means that some of the component of x, some of the frequency component of x would be blocked by the ideal low pass filter because beta is less than omega m, right? So this portion of the signal will be blocked from passing through. Only this portion would be able to pass through. So the output spectrum, the spectrum of the output will look like this. Here. Okay. This portion of the signal cannot pass through, right? So we have beta here, minus beta here, and this is minus omega m, this is omega m. The shaded portion cannot pass through. Okay. Oops, sorry. This cannot pass through. Okay, this cannot pass through. Okay, because filter blocks it. Because beta is less than omega m. But if beta is greater than omega m, then we know that all of x would be able to pass through. Okay, then y would be equal to x. All of them will be able to pass through. Okay, this is y. So this is an example of a low pass filter. So the function h of omega, which is defined as the Fourier transform of the impulse response, is called the transfer function, the frequency transfer function of the system. Not to be confused with the transfer function in chapter 3. So I include the word frequency here. Transfer function of the LTI system. Okay, and the output spectrum would be equal to the frequency transfer function multiplied by the spectrum of the input signal here. Now, uh, for low pass filter, ideal low pass filter, if the LTI system is an ideal low pass filter, then the transfer function would be, as we discussed, it is going to be the rectangular omega over 2 beta here. Of course, there are ideal high pass filter. Okay, high pass filter means it blocks low frequency components of the input from passing through, and it will let the high frequency components pass through. So ideal high pass filter has the frequency transfer function of 1 minus rectangular omega over 2 beta here. And we also have an ideal band pass filter. So a band pass filter is a linear time invariant system that lets a range of frequencies pass through and blocks the rest. So it is band pass filter, band pass filter. Okay, this is rectangular omega minus omega 0 over 2 beta plus rectangular omega plus omega 0 over 2 beta. So you can plot it, of course, the ideal bandpass filter. So if we plot it, the ideal low pass filter, ideal high pass filter, and ideal band pass filter. The ideal low pass filter looks like this. It is a rectangular pulse that only lets the lower frequency component pass through. Okay, so this is ideal low pass filter, and the ideal high pass filter is the reciprocal of the ideal low pass filter. So it is a trough here. Okay, now this is 1 and this is 1. This is beta minus beta. This is minus beta. This is beta. And the ideal bandpass filter is, of course, a rectangular that goes to the left and goes to the right. Now, the shaded area are the frequency range that the filter allow it to pass through. Okay, here. This frequency range can pass through, right? The rest cannot. The rest are blocked. This is omega here, and this is omega 0, and this is minus omega 0. Okay, and this is uh this is 2 beta. This is also 2 beta. Okay, ideal bandpass filter. Now, if we the impulse response of an ideal low pass filter can be determined by taking the inverse Fourier transform of this signal, right? And we could use duality to find that this is actually equal to beta divided by pi and sinc beta t. Okay, we talked about this already, okay, at the beginning of the class. And as for the ideal high pass filter, the impulse response can be found by taking the inverse Fourier transform of 1 minus rectangular omega over 2 beta, and by linearity this is equal to delta minus beta over pi sinc beta t. Now the delta comes from 1 here because we know the inverse Fourier transform of 1 is delta. And this guy comes from the Fourier transform of rectangular. And the last one, the impulse response of the bandpass filter, ideal bandpass filter, can be determined by taking the inverse Fourier transform of this guy. Okay, and this is just beta over pi, beta over pi sinc beta t, and then we have to use the frequency shift. If you remember frequency shift, yeah, this is frequency shift, right? Frequency shift. So in the frequency domain, frequency shift, in the time domain, this is just multiplication by complex exponential. So the inside is e to the j omega 0 t plus e to the minus j omega 0 t. Okay, and this is of course 2 cosine, right? So this is just 2 beta over pi and sinc beta t and cosine of omega 0 t. So this is the impulse response of an ideal bandpass filter. Now, the last property that I'd like to discuss is called uh, time multiplication or frequency convolution. Time multiplication. The last one that I'd like to talk about now, it is going to be property number 8 of the Fourier transform. 8 time multiplication. Now the time multiplication property goes like this. If we multiply two signals together, x and y, and we take the Fourier transform, okay, the result would be 1 over 2 pi, and Fourier transform of x convolution with the Fourier transform of y. Now the convolution has to be carried out in the omega domain, right? In the omega domain. Okay, and yeah, all right. I'm not gonna go. I'm just gonna leave it right there without any examples because you won't see this very often as you won't see this as often as the other ones. So yeah. So let me summarize what we've learned for you, right? Uh, so we have a Fourier. So suppose this time domain. Okay, on the left hand side is time domain. On the right hand side is the omega domain. Now the first one is the definition of the Fourier transform, and it is integration going from minus infinity to infinity x of t e to the minus j omega t dt. Now the inverse Fourier transform, I'm sorry, the delta signal has the Fourier transform of 1. Okay, and the DC signal of 1 has the Fourier transform of 2 pi delta. Okay, and e to the j omega 0 t has the Fourier transform of 2 pi delta omega minus omega 0. Okay, and then cosine, and then cosine of omega 0 t has the Fourier transform of 1/2 delta omega minus omega 0 plus delta omega plus omega 0. And this one I haven't talked about, but I'm just gonna give you the formula anyway. Sorry. Just gonna give you the formula anyway, the sign, which is actually this is pi. This is pi. The sign is pi over j and delta omega minus omega 0 plus delta omega plus omega 0. Okay, that reminds me that I think I made a mistake somewhere at the beginning of this lecture. I think it is this one. Okay, it has to be pi. Sorry about that. It has to be pi here at the beginning. It has to be pi. Okay, sorry about that. And the next one is, oh, I think I have to change this one to green. Color green. Okay. Now the next one is a rectangular pulse of width t. And the Fourier transform of it is t sinc omega t over 2. Okay. And we know that if we use the duality, then we have sinc beta t has the Fourier transform of pi over beta rectangular omega over 2 beta. All right, yeah. And the next one is triangular signal t over big T has the Fourier transform of t sinc squared omega t over 2. And of course, if you use a duality, you're going to find that sinc square of beta t has the Fourier transform of pi over beta triangular wave signal of omega over 2 beta. Okay. And is there anything else? And also, I haven't talked about it, but I'm gonna say it anyway. The unit step signal, I'm sorry, the signum function has the Fourier transform of 2 over j omega. This one I talked about, but the other one, which is ut, I haven't talked about. Ut has the Fourier transform of pi delta plus 1 over j omega. We haven't proved this yet, okay, but it's not very hard to prove because ut can be written as sinc plus 1, no, sinc plus 1 divided by 2, okay, and when we know that, the result will come out very easily. So this is a summary of the Fourier transform pairs in this course that you have to be concerned with. Okay, this is for your convenience. Right, and I think we are out of time. And are you guys here? Still here with me? Hello? Hello? Yes, all right. Uh, our next lecture will be on Tuesday next week because Thursday is a holiday, right? It's a long holiday, so we won't have we won't have class on Thursday, and we'll see each other again next Tuesday. But unfortunately, uh, next Tuesday, yeah, we might have to cancel the class next Tuesday, and we'd have to have a makeup class later. I'm gonna post post it on Classroom. So we may have to cancel class next Tuesday. I may have to go somewhere very, very important. And then I'll keep you updated uh, on Google Classroom. So we may have to cancel next Tuesday. We'll keep you posted. Okay, please check Classroom for any updates. All right, and then see you next time. See you next time. Please check Google Classroom for any update. And is there any question you'd like to ask? I'll post the clip of this lecture on Google Classroom. Please check it out. All right. And if there's nothing, uh, have a good holiday and take care. Be safe. Stay safe. Bye bye.